Welcome to The Explainer. Today, we're diving deep into the cognitive architecture that lets us build truly autonomous AI agents. We're going to move way beyond the basic models and really get into the memory and reasoning systems that are defining the next generation of AI. So, here's the plan. We'll kick things off by framing the core problem we're all trying to solve. Then we'll break down an agent's memory, looking at both short-term and long-term. After that, we'll get into the cool stuff, the advanced cognitive functions that actually use that memory, and we'll wrap it all up with a new blueprint for how you can design these systems yourself.
All right, to really architect an effective agent, we first have to get our heads around the fundamental challenge. How do we get from a stateless model to a truly stateful one?
Okay, so the core problem is this. We've got these brilliant large language models that are amazing in the moment, but they're fundamentally stateless. They're forgetful. The real engineering challenge is to evolve them into stateful agents, systems that can actually maintain context, learn from what's happened before, and carry out complex, multi-step tasks all on their own.
Now, it is absolutely critical that we distinguish this from RAG, or Retrieval-Augmented Generation. RAG is fantastic, but it's about looking things up, fetching information from an external, static knowledge base to answer a question. Agent memory is different. It's about maintaining an internal, dynamic model of the world that actually changes and evolves with every single interaction. It's the difference between looking something up and truly remembering.
So the first component in our cognitive stack is short-term memory. You can think of this as the agent's immediate, volatile context, where all the active processing is happening. Short-term memory, or STM, basically functions as the agent's working memory. It's like its scratchpad, a super fast but temporary buffer for whatever task is at hand. The catch? Its size is limited by the LLM's context window. And managing this finite space means you have a big architectural trade-off to make. On one hand, you have the simple sliding window approach. It's fast, it's cheap. You just pass in the most recent data. On the other hand, you've got something more sophisticated, like a summary buffer, which uses another model to compress the context. This gives you much higher quality context, but it comes at a cost of more latency and more compute. And that brings us to the really juicy stuff, long-term memory. This is what's critical for any real learning and continuity. And for a while, the central debate in how to build this has been a kind of paradigm war between different ways of storing information. So first up in this war, you have vector databases. These are perfectly optimized for what we call episodic memory. They allow for semantic or fuzzy recall. This means an agent can retrieve information based on conceptual meaning, not just keywords. Think of asking, what were the key points from our last conversation? That's a job for a vector database. Next up, we've got knowledge graphs. Now, these are built for relational memory. They don't just store individual facts, they store the connections between those facts. This is huge because it allows an agent to perform what's called multi-hop reasoning. For example, it could navigate a whole network of academic papers to find the one that started it all. It's all about understanding how things are connected. And finally, we have our old friend, the traditional SQL database. This is the foundation for structured, factual memory. It's essential for storing precise, auditable data that absolutely has to be right. Things like user profiles, permissions, or hard-coded business rules. So this table really lays out the whole landscape. You can see each one serves a very distinct cognitive function. You've got semantic recall, relational reasoning, and factual precision. The key insight here is not that one of these wins. It's that each one is a specialized tool for a very specific type of memory. And that leads us to the big conclusion here. The paradigm war is over. The best solution isn't to pick one database and stick with it. It's to build a hybrid architecture that intelligently uses all three. This lets the agent pull from the right kind of memory for whatever task it's trying to accomplish. Okay, so we've got the memory storage in place, but that's just one piece of the puzzle. How does an agent actually use all this memory to think and reason its way through complex problems? Well, a key innovation here is something called the reflection mechanism, which is actually modeled on how our own brains work. It pairs two modules, a fast, low-level one that does all the detailed number crunching, and a slower, high-level one that synthesizes insights and forms abstract plans. So you get this incredibly powerful loop of execution and then reflection. Doing, then thinking about what you've done. And this leads to an even more advanced pattern, agentic memory. This is where the memory system itself basically becomes an autonomous agent. It's not just passively storing stuff anymore, it's actively curating its own knowledge base, making smart decisions about what to keep, what to update, and what to throw away to make itself more useful over time. So let's put all these pieces together into one unified blueprint for what a modern cognitive architecture really looks like. A truly robust cognitive architecture integrates these four key layers. You need a well-managed short-term memory, built on top of a hybrid long-term memory store. You need a hierarchical reasoning engine for that deep thinking, and it all needs to be maintained by an agentic curation layer that's constantly making the knowledge base better. So the key takeaway is this. Building advanced AI agents requires a real shift in our mindset. The challenge isn't just about picking a database anymore. It's about designing a complete, multi-component cognitive architecture. That is the blueprint for creating agents that can truly reason, learn, and adapt.